Okay, so there's several concentration units that we're going to have to go over. This is three of the concentration units that are based on moles. We have the molarity, which you should be familiar with. That's the number of moles of solute divided by liters of solution. And again, the solution is the solute and the solvent combined. But then there's molality, which we'll come across here. We'll be using it at the end of the chapter when we start talking about something called colligative properties. And another concentration unit is osmolarity, and this is what you see a lot in medicine. It's the concentration used to describe the number of solute particles that are in a liter of solution. So it's very similar to molarity, but the moles of solute particles don't have to necessarily be the same as the moles of substance. For example, sodium chloride, when it dissolves in solution, produces sodium ions and chloride ions, and osmolarity takes that into account. The difference between osmolarity and molality, that's what the molality is the middle one, is that instead of being over liters of solution, it's for kilograms of solvent. So in general, molarity is moles over volume of solution, and molality is moles over mass of solvent. So they're a little bit different. And osmolarity is very similar to molarity, except it takes into account the number of solute particles. So we'll do a couple of examples. Quick example, calculating the molarity. It says calculate the molarity of a solution when 14.2675 grams of sodium chloride is dissolved in water to prepare 250 milliliters of solution. And to calculate the molarity, all you need to do is remember the definition. It's moles over liters, right? So what we need to do is find the moles and the volume in liters, and then we can calculate the molarity. So 250 milliliters can be quickly converted for the purposes of doing these kinds of calculations simply by substituting the prefix 10 to the minus third and leaving the liters behind. So this is, even though it's not proper scientific notation, this is what the number 250 milliliters represents. And then now we need to calculate the moles represented by 14.2675 grams. So if I take 14.2675 grams and I want to convert that into moles, I just need to divide by the molar mass, which is given, 58.443 grams for every 1 mole. And that gives us a concentration of 0.976507. It goes on for quite a while, moles per liter. In this problem, we have 4 significant figures in our volume and more in both our molar mass and our mass. So we're going to keep this down to 4 sig figs. So this comes out to 0.9765 moles per liter. Next, we'll look at a calculation for essentially the same numbers, but we're going to calculate the molality of that solution. So in calculating the molality, we need to think about our definition, but we're going to calculate it. Again, this is the same numbers for the solution that we're talking about here, but we need to do it for a definition of moles per kilogram of just the solvent. So if we take a look at what we've been given here, right, we have 14.2675 grams. Now the moles that we get out of that will be the same, but the question is, how much solvent do we have? Well, what we're going to do is we're going to take advantage of the fact that they give us the density. And what we can do is we can, from the density, calculate the mass of 250 milliliters of solution. Once you know how much the solution weighs, you can subtract out the sodium chloride and figure out how much solvent was used to prepare that solution in terms of grams. So our solution mass we can use the 250.0 milliliters and the density and calculate the mass of solution, 1.0359 grams for every 1 ml. That's 258.975 grams. We have 4 sig figs at this point, so I'll just mark it there. And then the solute mass, or the solvent mass, will be 258.975 grams minus the 14.2675 grams of sodium chloride. That leaves us with 244.7075 grams of solvent. Now, molality, to do our calculation, what we're going to start with is we have 14.2675 grams, and then we need to convert the 244.7075 grams into kilograms. Again, let's see, we have significant figures to this place here. So what we're going to do is put 244.7. Let's carry a couple of extra digits, but marking 4 sig figs there, marking 4 sig figs there. This is grams. So there's 1,000 grams for every kilogram of solvent. That'll allow us to cancel this out, and then let's choose a different color to make it a little clearer. We can convert the grams into moles by going 58.443 grams per mole for sodium chloride. So that will cancel that out. That leaves us with 0.9976, and then the unit comes out to be moles per kilogram solvent, which is abbreviated M, like that. So if we compare actually this molality, because remember this is the same solution that we talked about in this problem, but instead of reporting in molarity here, we did it as molality. It's 0.9765 molarity units, moles per liter, and slightly different 0.9976 molality units. And if the concentration had been higher, this would have been even more, these two numbers would have even been more different. Okay, so it's important to keep track of which unit you're using, but regardless of the type of unit, really just goes back to the definitions of the units and then look at the information you're given to try to figure out how you're going to get those values. Another really common set of units are the parts per set of units, and it can be parts per 100 or parts per million or parts per 1,000, and it can be done either by mass or by volume. Now, when the calculations are done by volumes, then you'll often see something like this. If it's done by mass, you usually see M over M, like this. Or in some older literature, you'll see W over W, because what they're saying, this is mass over mass, this is weight over weight. So these should be considered to be, for the most part, equivalent. So what is a part per 100? That's the percent by mass of the solute in the solution. So let's say you had a 5% solution, and it's weight, or mass by mass. What that means is I have 5 grams of solute. So it's by the mass of the solute, not by the moles, for every 100 grams of solution. So The other way you can look at it, though, and this is actually really useful in doing a lot of the calculations you have to do with percents or per millions, whichever unit you're working with, is to think of it as 5 grams of solute over 5 grams of solute plus 95 grams of solvent. Because they have to be per 100, you automatically know what the solvent percentage is if you know what the solute percentage is, assuming there's only 2 components, right? So they have to be part of 100. Now, if you were doing parts per million, right, then it would be 5 grams of solute over a million grams of solution, and then it would be 5 and then 999,995. Right, so it would be something like that. Anyways, but this is a very useful way to think about it because now you know the ratios of the mass of solute to solution, but you also know the mass of solute to the solvent. It's 5 parts for every 95. And when we're doing these calculations, you'll see being able to see these parts per units as breaking them into their components is very useful in doing the calculations. Now, parts per million is essentially the same calculation as parts per 100 or percent. It's just that we multiply by million. So it's assuming if you had 1,000,000 grams of solution, how much grams of solute would you have in that solution? Now, parts per million can also be, and parts per 100 can also be expressed as volume percents. So part per million as a volume percent would be solute volume divided by the solution volume. And this is the kind of concentration unit that makes sense when you're dealing with liquid solutions. So if you're taking a liquid and then dissolving it into another liquid, percents by volume are often the best or easiest way to describe those. The most common one that you see is in alcoholic beverages or alcoholic solutions like rubbing alcohol. They list the percent, and that's actually a volume percent. So when it says a beer is 5% alcohol, that means there's 5, like this 5% ethanol, for example. It would be listed as volume. That's 5 milliliters of pure ethanol for every 100 milliliters of solution. Now, it is really tempting to say that 100 milliliters solution would be 5 mils of ethanol and 95 mils of water, but it turns out solution volumes don't add the same way that masses do. Oftentimes, because of the intermolecular forces that we're talking about in solution formations, the densities of the solutions change when they're made, and so you get different volumes. They're not additive. So 50 mils of ethanol and 50 mils of water only comes out between 90 and 95 milliliters of total solution volume because the density goes up, so it's held in a smaller volume. So here we're going to calculate the weight percent. Like I said, often it's listed as mass over mass, but this is a weight. I've written it as. We're going to calculate the weight percent of sodium chloride solution containing 30.7 grams of sodium chloride in 123.5 grams water. So in order to calculate the percent, I'm going to go ahead and say, well, I have 30.7 grams of solute, right, NaCl. And then I have a total, I'm going to write it like this, but you can add these, it turns out, right? You don't have to write them out like I am here. 123.5 grams of water, like this. So this is your solution mass. And to get it to be a percent, then you just multiply it by 100. So when you go ahead and you do that, what you end up with is 19.909%. I have 3 sig figs here, so I'll round it to that point there. and I'll end up with 19.9% sodium chloride solution. So here's another problem. It says, how many grams of water do you need to be added to 5.55 grams of sucrose to get a 10.5% sucrose solution? So the way you do this problem is you have to think to yourself, I need to know solution volume. That means I'm going to take the 10.5% and break it down into its component. It's 10.5 grams of solute for every 100 grams of solution, but it could also be written a couple of different ways, and I've just sort of taken the liberty to write them out already. It could be 10.5 grams of solute for 89.5 grams of solvent, so basically I just took the 100 and I subtracted the 10.5 from it. Or it could be 85.9 grams of solvent for every 100 grams of solutions. There's a lot of ways to look at this kind of problem. So if you wanted to get a 10.5% sucrose solution out of this, that means you need to know the mass of the solvent that goes with the 5.55 grams. So in order to do that, we're going to calculate mass of solvent. So I'll start with the 5.55 grams. And then it's 89.5 grams of solvent. That's a V. For every 10.5 grams of solute. That's a U there, okay? So then I can get these units to cancel, and this will tell me the grams of solvent that I need, and I end up getting 47.31 grams of solvent. Now, if you're actually doing this in a lab, what you normally, so this, just to back up here, if you have the 5.55 grams, right, you can add the 47.31 grams of solvent to it, and you should get a 10.5% solution. Now, if you're doing this actually in a lab, what you actually calculate is the mass of the solution that you need. So we would just do this. This is mass of solution. And we would take 5.55 grams, and then we can use the mass percent directly. We can say 10.5 grams of solute for every 100 grams of solution. Just abbreviate it like that. And that gives us 52.857 grams of solution. Now the reason we do that typically in the lab is the way we make the solution isn't to take the 5.55 grams of sucrose and then measure out 47.31 grams of solvent. What we actually do is just put the 5.55 grams of sucrose into a container that's been tared, and then we just add water until we get to 52.857 grams. Probably should be rounded to that place there, actually to this place here. Now, if you're curious, right, if you take the 5.55 grams and you add it to the 47.31 grams, right, this is the solute and this is the solvent, it adds up to 52.857. So a quick check on your work is always simply to take the mass of the solute and the solvent that you calculate and add them together, and those should be the mass of the solution. So I thought I'd show you a couple of parts by mass examples of how we calculate parts per million and how we might use like a parts per mass unit to calculate how many grams of substance are actually in a liter of water. So CDC has set a threshold level, action level for lead that's 5 micrograms per 100 milliliters. Now, there's actually no known safe level for lead. Interesting thing happened in the 70s, I remember, is everywhere started suddenly reporting lots and lots of lead in drinking water, in the environment, etc. And a lot of that had to do with the fact that gasoline had lead in it. But another thing happened is that people got really good at detecting lead. So when we didn't think there was lead, we didn't worry about it. But as soon as we got better detection methods, we were suddenly realizing lead has sort of infiltrated everywhere. It was also in paints, and so children were often eating the paint. And then excessive lead leads to things like brain damage, neuronal sort of disorders. Anyways, we're going to figure out how many parts per billion 5 micrograms per 100 milliliter represents, because it doesn't sound like a lot, right? So parts per billion, P, get my pen to work, ppb represents grams, right? We would take the mass of the solute, so in this case of the lead, and we would divide it by the mass of the solution, and then times, now billion is 10, right, to the ninth. So we multiply by 10 to the ninth, and that would give our parts per billion. So 5 micrograms is 5 times 10 to the minus 6 grams. 10 to the minus 6 being the prefix for micro, right? So we can write it in scientific notation like this. I guess I should write it as 5.0. And then I would divide it by the mass of the solution. And this is actually something that's done a lot in environmental studies, is we just assume the density of the solution is going to be 1 gram per milliliter, and for the most part that's pretty close. So 100.0 milliliters would be 100.0 grams. And then we multiply by 10 to the ninth. And this comes out to 50 parts per billion. So in another example, what we're going to do is we're going to calculate the micrograms of chromium that you would see at the action level for chromium, which is set as 100 parts per billion. So it's actually a little bit higher than this. We're going to calculate the micrograms of chromium that you would find in 1 liter of water. So we make a couple assumptions when we do this calculation. Here's the first one. It's the same as the one that I was talking about here in essence. I have 1 liter of water. That would be 1,000 milliliters. And then that would be the same as 1,000 grams, because we're assuming the density is the same. Now, if the density is not the same, or specifically they give you a density other than 1, then what you have to do is you have to take the density into account in this step of going to milliliters to grams. But we're going to assume, right, 1 liter is 1,000 grams. The other thing that we do is we say, what does 1,000 parts per billion or 100 parts per billion mean? And what we do is we say, well, that means there's 100 grams for every billion grams, which is 10 to the ninth grams of the solution. So this becomes our conversion, just the definition of parts per billion. So like parts per 100, right, percent is grams per 100 grams, for example. So in parts per billion, we're going to be doing grams per 10 to the ninth grams. And so what we can do now is we can calculate the grams of chromium in 1 liter of solution, and then we're going to convert that to micrograms. So we're going to go from liters to grams, which is what we've already done, of solution. And then we're going to go to grams of chromium, and then we're going to go to micrograms. Okay, so I'm already starting at this point here. So I have 1,000 grams of solution, and then it's 100 grams of chromium for every 10 to the ninth grams of solution. And then I know that 1 microgram is 10 to the minus 6 grams, like that. And so when I do the calculation, it comes out to 100 micrograms of chromium would be in the water. Okay. And it makes sense if you think about the numbers that I gave here, and I got 50, and the numbers that I was given here, I get 100. Okay.